Thank you very much for your very kind introduction, Juliana, and I'm really happy to see all of the green chemistry community here today. Thank you for being present. I will jump right into this work, that before I go there, I'd like to acknowledge that I'm presenting from Newfoundland and Labrador in Canada, and I acknowledge that the land on which I present from is in the traditional Mi'kmaq territory. I acknowledge with respect the diverse histories, cultures of Beothuk, Mi'kmaq, Inuit, and the Innu of the province. And because we're presenting online remotely, I acknowledge the diverse histories and cultures of Indigenous peoples from coast to coast to coast. Before I head off, I have some thanks due to a lot of people for this, especially the students of my 4th year course in Green Chemistry and Sustainable Synthesis at Trent University, who did this work, and their passion was evident. Dr. Punnasamy from Millipore Sigma and Caleb Vetter, who was at that time an intern with Millipore Sigma, their support was imminent to this work. Really grateful for their support. And I'd like to also thank Kyle and Kyla, who are both undergraduate authors on this work. They were in the course, did it from the student end of it, and they are here present on this call today. So if you have questions on how the students worked in groups and did this work and received it and did it virtually during the pandemic, I'm sure they'll be very happy to answer your questions in the chat or in the breakout rooms. Thank you, Kyle and Kyla. So we all are familiar with the fact that students really are passionate about learning and then taking their learning forward to sustainable futures. Their sustainable future, the planet's sustainable future, but they feel under-equipped and actually unempowered without the practical tools that help them become sustainable decision makers. And on the flip side, from the industry wants something that is easy for assessment, improvement, implementation, and they want employment-ready skill sets that come in from academia or from education. And so this work, we were trying to bridge that gap and provide those practical tools, a group of tools that would be complementary, and then prepare students with employment-ready skill sets by integrating these tools into the learning and teaching during the course. And of course, because the demographic of the class was 4th year students entering into academia or industry, they were at that cusp, especially at a transition time when virtual presentations and virtual life, a whole new way of communication had become ingrained in our lives. We wanted to help students develop excellent but accessible communication skills in science. So putting all of that together, effective chemical decision-making sounds pretty daunting and required a whole systems lens, a holistic view that not only made them critically rethink chemistry practice, the use of copious amounts of solvent. And thank you to Philippa, who's really giving the segue from PMI into this conversation, and you'll see the connections happening. So rethinking the solvents, poisonous, hazardous chemicals, catalysis, endangered elements for catalysis, waste generation, all of this to designing at the molecular level so that we reduce or eliminate hazard completely, but then for effective chemical decision making, taking those connections from chemistry, chemical reactions, reagents to people and planet, to integrate, say, interdisciplinary knowledge, diverse viewpoints, and what are these challenges for people and our environment, socioeconomic and environmental challenges. So this requires that we look at this whole chemical decision-making from a systems approach that has a group of complementary tools that can assess, improve, and make implementation convenient and relevant. And so to do that, what we tried to do was integrate projects at a summative assessment level, where we gave our students, through the course, they learned about quantifiable green metrics, life cycle assessment. They were introduced to reinforcement and balancing loops and some systems thinking terminology. And then we asked them to look at 2 reactions that created the same product. And I will be introducing those projects in a bit. They applied green chemistry metrics, quantifiable green chemistry principles. They looked at those computed values and compared them and assessed against life cycle assessment metrics. Those were multivariate metrics as well. And then they took all of those values and fed them into an understanding of how they impacted or connected to United Nations Sustainable Development Goals, put on the systems thinking lens, and then looked at trade-offs, economic impacts, socio-economic environmental impacts, to arrive at a decision on what of the two pathways should they actually recommend, or if there were any innovations, substitutions, green chemistry modifications that they needed to make. And so the metrics that were introduced during the course, here are some green chemistry metrics. They looked at atom economy, the E factor for the waste, and of course, the process mass intensity that Philippa's just introduced us to through her work. And what we did was we asked them to look at those, calculate those values. But the thing that they came up with, that all of these sustainability green chemistry metrics tied up with the mass of the product. So we're looking at now waste tied to mass of product. We're looking at process efficiency tied to product, and the yield, which is in a way a reductionist way of looking. And therefore, we needed them to think of it in a more multivariate approach, still using green chemistry principles. That is where DOZN 2.0 became a very useful tool for us, introduced by MilliporeSigma, used by industry professionals, but free for us to register and access. So our students registered for it and took these 12 principles that are qualitative in nature. And these 12 principles, MilliporeSigma DOZN 2.0 has divided into 3 categories, or 3 major groups of resource use, energy efficiency, and reduced environmental and human impacts. So these groups have their own scores, which quantify these qualitative principles and then help arrive at an aggregate score for each group. Now, you want to have an aggregate score which is closest to 0, indicating minimum or signifying minimum impact. And therefore, you want 0 for an aggregate score, but 100 being the maximum. And what we really enjoyed with this tool was not only it quantified the green chemistry principles, but students were able to take a standard safety data sheet, so easily accessible. Every chemistry student is introduced to it when they go into laboratory. And that safety data sheet actually allowed them to use for biohazard scoring, which looked at the aquatic toxicity of the chemical and gave it a score from 4 to 1, 4 being the most toxic. And using these different quantifiable metrics, actually a value, they could compare their reaction pathways. But what happens when you have something that seems very similar? And that's when they also used life cycle impact indicators, which actually help them look at not only green chemistry principles from the reaction process pathway, but also the impacts on the environment for global warming, acidification potential, bioaccumulation. Now, all of these equations and calculations were introduced to students during the course. They had practice, they had examples. And so by the time they came to this project, they were familiar with these. These are easily accessible, and whatever information they required was either available through literature or through handbooks of chemistry. And so when they got all of that data together, they connected green and sustainable thinking, circularity thinking based on waste, life cycle thinking, and then connected them to the environmental impacts and socioeconomic impacts and how those impacted the wider global issues with United Nations Sustainable Development Goals. So the projects, as you can see, there are 2 projects that I've highlighted here first. They are starting with the same starting materials. In this case, project 1 is the synthesis of hexane nitrile. Hexane nitrile is industrially relevant for fragrance industries, and you can see for benzophenone, which is also useful for pharmaceuticals and the fragrance industry. We just had a presentation for the Green Motion, which is for the fragrances. So this is all tying in beautifully. Now, starting from the same starting material to the same product, using 2 different pathways. The pathways have different reagents and different reaction conditions, but also different byproducts. And so applying that thinking, the reductionist method would have said, 97% yield, hexane nitrile, pathway 1, perfect, let's go with it. Let's go and do this reaction this way. But now using the complementary tools, students were really thinking about more than just the yield or the efficiency of the process, and how they could use the byproduct and bring it back into circular design. Although a lot of that required integrated thinking, but you can see that all 4 projects had materials that were industrially relevant. So this is one of the student projects for benzyl hydrol synthesis, which is project 2. There were 2 pathways, route C and route D. And the green chemistry metrics, the process mass intensity, E factor, atom economy, and the percentage yield clearly said that for atom economy and higher yield, go with route D. We get 70% and we have a great atom economy. But when you put the E factor and the waste, you realize that route C actually is better. So now that creates a confusion, but also the knowledge that something that looks atom economical can be wasteful and inefficient. And therefore, how do you decide which route to take? And that's where then the multivariate metrics, moving away from that univariate mass-based approach, allows them to go to the sigma dozen tool. This is an actual screenshot from where the students input their data. And here it tells you that KMNO4 versus the bleach oxidation, the aggregate score for bleach oxidation is just 2 versus 28. And so it's clearly identifying that the route 2 is the route D, which is the better, greener route, also has better energy efficiency and is safer for and against the accident prevention and accident prone synthesis. So it's reducing hazard there as well. Now it's giving a direction in this case. And so you can see that using the green metrics, which are only mass-based, students find that very useful. Now you look at this pathway A and B, and you find that there is a huge waste. There's a magnitude of difference when it comes to E factor and process mass intensity between the two. Very clearly, you can identify route B versus route A. And you can see here that both of these are pretty fairly close, but route F beats route E by a little bit. So how do you put this together with the multivariate metrics? And here you will find that if you had to compare between route E and route F by the univariate metrics, the green chemistry metrics, it would clearly be route F. But then when they do the complementary analysis with sigma dozen, they find that route F actually is slightly worse than route E. And really, this kind of identifies that where do you think it must have been the problem? And so if you look at the E factor for F, it's 24.6, seems to do better on this waste. But then if I look at the waste prevention by the green chemistry principles, actually, this is where you find that the smaller amount has a higher severity. And so looking at the severity of the waste becomes important and allows the student to make that decision about whether we should go with route E or route F. Now, route E and route F both have a very low aggregate score. So as such, they would be pretty equivalent. Like, doesn't matter so much about E. You are going to have to take a trade-off decision. Am I going to do E or F? How do you decide? And that's where then the LCA metrics become very helpful in complementary analysis. And you find that route E actually has smoke formation, but route F has acidification potential, is persistent, and it accumulates, bioaccumulates. So really, it is helping you take a very clear, confident move towards route E rather than route F. And it also tells you that route F has a slightly higher aggregate score, but it has high environmental impacts. So similarly, doing a comparative complementary assessment using now sigma dozen and LCA, what we find that with route A and B, if you look at the LCA metrics and the sigma dozen tells you A is clearly better, 100 versus 4. That's the one you should do. But route A by LCA gives you hotspots for analysis, that if I were to improve the global warming potential and the persistence of the chemicals here, then I can actually use A and innovate, improve, substitute for these two particular areas of environmental impact. And then if you look at group roots C and D, and you will find that D does really well compared to C, 28 versus 2 by sigma doesn't. But if you look at the life cycle impact assessment indicators, they're pretty similar, which means you are going to have to make a decision of trade-offs and priorities between environmental impacts versus resource use. And if you look at G and H, you clearly see that G is better than H, 100 versus 3. But in H, you are going to look at 2 hotspots of inhalation and ingestion toxicity versus global warming. And that allows you to build confidence in implementation of root G by just working on the global warming potential and doing some substitution innovation or some kind of real improvement in that area. And so here's another area where students work together. They calculated the economic impact. How much does it cost per gram or per kilogram or per mole of this? And it was divided out based on the yield they saw for each of those reactions, and actually arrived by putting those in perspective with the other impacts. And they connected all of this information to where these impacted the wider global challenges. And you can see that many of those routes have multiple connections. And seeing those connections really allows students to see the role of themselves as chemists in an equitable world. So it was a very interesting area of discussion for students to see how it connected to other areas beyond just, this is my reaction and this is my yield. And they also recommended substitutions. And you can see they found both the pros and the cons. Solvent-free versus non-renewable. Solid reaction mix, no derivatives versus non-degradable. And so they recommended these things and looked at both the pros and cons, which is very interesting. And finally, we asked students that did they find that they were able to feel better equipped with these complementary tools? And very well or well-equipped was their answer. So we do feel there is confidence in bringing this kind of learning into our classrooms. And then we asked them, were these tools helpful to prepare them for a sustainable future? And you can see either it's a yes or an overwhelming definite yes. There were no on the border thinking with this. So clearly it has been very beneficial to them to prepare them. And lastly, we asked which of the tools was easiest for them. And here the interesting part was that systems thinking was not as intuitive, but life cycle thinking and DOES&TM, which actually allowed them to get absolute values to compare, were way more interesting, easier to understand and follow through. So that means somewhere we have to bring in systems thinking into our curriculum earlier, introduce it at some levels where we are giving them the terminology, the thinking, the life cycle comparative, all of this earlier in their course and learning. I thank you for your attention, and I'm happy to take any questions.